Welcome back, everyone. I hope you are ready for advanced methods in molecular dynamics. Tomáš, take it away.
Thank you. All right, so this is the second lecture on molecular dynamics, where we deal more with advanced molecular dynamics methods. Before we immerse into that, so we start a little bit with the theoretical background that we need to understand the basic ideas behind this methodology. So we shall talk about kinetics of activated processes and about Helmholtz free energy. Then I will introduce, so basically I will make presentation of advanced molecular dynamics methods aiming at free energy calculations that are presently available in VASP. So that will be umbrella sampling, umbrella integration, Blue Moon ensemble method, and many others. And finally, in final part of my talk, I will talk about one specific problem, efficiency of molecular dynamics simulations, and I will discuss how machine learning can help to improve the efficiency of MDs. Okay, so this is the theoretical part, kinetics of activated processes. So let us consider the simple possible reaction ever, which is transformation of reactant to product. Okay, simplest reaction. Okay, now the rate at which such a reaction occurs is expressed as time change of concentration of product, Cp, and this is proportional to the concentration of reactant, Cr, and the proportionality constant is called rate constant. Within the transition state theory, this can be expressed by famous Eyring-Polanyi equation. So if you look at that, you see that in addition to physical constants and temperature, there is only one physical quantity, which is free energy of activation. Okay, what is that? If you look at typical energy profile, be it free energy, potential energy. So if you look at energy profile of reaction, it typically looks like that. So the stable states are confined within certain kind of valleys, right, which are separated by barrier. So the presence of barrier is there because, of course, in order to convert one stable state into another one, you have to temporarily destabilize the system. You need to break some bonds, maybe you need to do some skeletal deformations, right? Okay, so when you do so, you increase energy until you reach the top of barrier, which is transition state, right? And from this point on, you start to stabilize system, you form bonds, you do skeletal relaxations and things like that. And the activation energy that appears here, so free energy of activation in these terms, would be free energy difference between the top of free energy barrier and reactant state. Okay. So maybe you are not interested in kinetics of chemical reactions. Okay, so well having rate constant, this gives you access to kinetics. Okay, so having this, you can say how fast the reaction is, right? But maybe this is not what you are interested in. Maybe you're rather up to determining free energy difference, or well, you're up to predicting equilibrium concentrations of or relative equilibrium concentrations of reactant and product. Okay, so these proportions, that is expressed by quantity called equilibrium constant. This is ratio between equilibrium concentration of product versus reactant, which can be expressed in terms of partition functions. And as we see in a minute, this can be rearranged into this form, where once again, in addition to physical constant and temperature, there is only one more physical property, which is again free energy difference. This time free energy difference between reactant and product. So you see the free energy is a key quantity which give you access to both kinetics and equilibrium concentrations or equilibrium populations of stable states. And well, the molecular dynamics methods I'm going to talk about now in this second lecture are all about this property. Before I proceed, I need to define one special reaction, a special geometric coordinate. It's called reaction coordinate. So you see energy is so that we discussed is expressed as function of something, and that something is reaction coordinate. That's some coordinate that is able to drive the system smoothly and reversibly from stable reactant over transition state to product, and do so that basically the process can be reverted at any point, and you would basically proceed via exactly the same kind of path. And progress of reaction could be uniquely monitored by basically value of reaction coordinate. Okay, so depending on the particular context, you might see in literature different but related terms like collective variable and order parameter and things like that. Unfortunately, reaction coordinate, fulfilling those properties, being reversible, smoothly driving reaction and things like that. Unfortunately, this is not quite easy to find in general. In fact, this is quite a difficult thing. Throughout this lecture, we will suppose that we already have it. Okay, we are given the reaction coordinate, and we only think of how to make it use in free energy calculations. If you're interested in in this problematics, how can one test whether the candidate coordinate at hand is appropriate or not. So I would recommend you to read this excellent review paper by Baron Peters. All right, so let us consider, I mean, from this point on, I will adhere to canonical ensemble, okay? Many things I'm going to discuss could be generalized to isobaric isothermal ensemble as well, but I choose to discuss a canonical ensemble only. And within that ensemble, the relevant thermodynamic potential is Helmholtz free energy. It's defined like this. This is internal energy minus temperature times entropy. This differential form from which you see that the natural variables of Helmholtz free energy are volume, temperature, and number of particles. Okay, hence NVT. And the remaining parameters, remaining variables, thermodynamic variables, can be obtained via partial derivatives with respect to natural coordinates, pressure, entropy, and chemical potential. Okay, so by analyzing changes of free energy, you can say whether a process is spontaneous or not. In the former case, you see that free energy decreases, in the later it increases, and in the case of equilibrium, free energy reaches its minimum at stationary state, so delta A is 0, for instance. Now in statistical mechanics, Helmholtz free energy is defined via this defining equation. It's related to logarithm of canonical partition function, and by comparing with the expression which we discussed in our first lecture for an observable, you see that the expression for free energy cannot be cast into the form of an ensemble average directly. You cannot do so, but so making the calculation of free energy, this is one of the reasons why this is challenging. You cannot obtain it just in the usual molecular dynamics run directly. Well, we can generalize the concept of Helmholtz free energy by introducing dependence on some geometric parameter, psi. Okay. We do so by first introducing this dependence into the canonical partition function. So this special type Q of psi is basically a partition function for all states with fixed value of psi, of parameter psi at certain specific value, right? So now if you plug that into defining equation, you basically get psi dependent free energy. Now it is easy to see that this partition function is intimately related to probability density. Okay, it's you can by simple rearrangements you can see that probability density can be expressed as psi-dependent Q over partition function. Now, combining these two equations together, you can see that free energy difference between two states characterized by different values of psi2 and psi1, which are nevertheless connected by psi, which is assumed to be reversible path. So then the free energy differences can be computed from probability densities. Okay, so probability densities and free energies are closely related quantities. All right, so now let us try to derive expression for free energy of activation and free energy differences that can be used in molecular simulations. Okay, to do so, we start with general transition state theory expression for rate constant. Yeah, transition state theory. That's basically the assumptions behind this theory are that there is something like transition states and quasi state, which is in equilibrium with reactant. Yeah, this is quasi state on top of the barrier, right? And whenever you reach transition state, starting from reactant, you inevitably fall down towards product. So if reactant is on the left, which I assume here, then any positive flux through dividing surface will lead to product. Okay, this is basic assumption of transition state theory, which is mathematically formulated here. So what you see here, this is basically partition function of reactant. So basically everything to the left from transition state, psi asterisk. Okay, and in the numerator, you have basically, you select transition state configurations and you average over initial velocities of psi such that they are positive. Okay, so this Heaviside step function chooses positive velocities and sets negative velocities to 0, right, as required by transition state theory. Now we can rearrange this very simply. First of all, we take into account symmetry because psi dot, that's speed on top of barrier, the sign positive and negative sign can occur with exactly the same likelihood. So you can replace basically this product by absolute value of psi, 1/2 of absolute value of psi. That's simple. And then we just extend, we just multiply and divide by the same term. First, this is basically partition function for transition state, right? And this is that for arbitrarily chosen reference reactant state, right? We multiply and divide by the same term, so we can choose it arbitrarily at our will. Now the terms as they are arranged, they can be expressed elegantly because the first term here, this is nothing but velocity at the transit, I mean absolute value of velocity at the transition state, the first term. The last term here is probability density of the reference reactant state, arbitrarily chosen. And this term here in the middle, that's reversible work needed to shift the state from reference reactant state to transition state. Okay. Now, by comparing this formula, which we just derived with Irving-Polanyi equation, we find the final expression for free energy of activation. Here, these three terms need to be determined in independent molecular dynamics simulations, as we shall discuss in a minute. We can combine free energy of activations for forward and reverse processes, right? So to express free energy differences between two stable states, product and reactant. Okay, this is just free energy of activation for forward minus for free energy of activation for reverse process. And if you do so, we realize that absolute value of velocity is identical for both processes, so this term cancels out, and what remains are again similar terms as we had here. So we have this reversible work, and here we have probability densities for arbitrarily defined reference states. Okay, so now let's discuss one by one these terms that we need to compute in order to have access to free energy differences. So the easiest one, I guess, is is probability density. We discussed the general procedure to determine histogram approximation to it. Okay, so this is what can be applied. So all you have to do is just run straightforward molecular dynamics, as we discussed in first lecture, for a reactant state, and choose the reference state arbitrarily, but it's always a good idea to choose it such that its probability density can be determined with good precision. So obviously that is state which is well sampled, so that should be state that is close to maximum of histogram ideally, but you're not bound to choose it like that. It's just a good idea to do so. Right. The next term is the velocity. So let's suppose that free energy transition states, ensemble of free energy transition states has been already determined because we do so in computing this step. Let's suppose we already completed that. We have ensemble of transition states. Now the calculation of this term is very easy because it doesn't even require any additional DFT calculations. All we have to do is just express velocity, which depends in internal coordinates, which depends on basically velocities in Cartesian coordinates times this Jacobi term, and this is position dependent, right? So for ensemble of transition states, you generate this, and you generate Cartesian velocities. You draw them at random from Maxwell-Boltzmann distribution. You compute psi dot, and you average over many structures and many randomly generated velocities. So computationally, this is very easy. This is not heavy calculation. The most problematic term is this one, the reversible work, and here is why. So yeah, naively you might think, okay, so well we have formula that relates probability density to reversible work, so why not to apply it? The problem is that the probability density at transition state appears here. Now, what's the problem, right? So if the barrier for a process is larger than the KBT term, which is often the case, right? So then of course probability density at the top of barrier is low. Let me give you an example. Let's consider a rather modest barrier of 50 kilojoules per mole. I mean, this is not particularly high. I mean, you easily find reactions where the barriers are over 100 kilojoules per mole or even 200 kilojoules per mole. Now let's consider temperature of 300 K, right? So using relation between densities and free energy, you easily find that the ratio between probability density at transitions at top of barrier and reactant is 10 to minus 9. So this state is many orders of magnitude less likely to be generated than this state, right? And practical consequence of that is that when you start molecular dynamics in a stable state here, so you will be locked there for all time. I mean, probably for your lifetime, right? So that's why reactions are said to be rare events at the scale of computer simulation. Okay, so in order to overcome this problem, to be able to sample transition region, we need some specialized techniques, and this is what I'm going to talk about. Now, there are several ideas how to tackle this time scale problem. Okay, so we keep in mind that our main problem is basically presence of barrier. So how about removing the barrier, right? Let's remove the problem, and the sampling should be easier. One way how to do it is basically to add to your actual potential, which you, by the way, don't know a priori, but let's say, I mean, conceptually, you can think of it, right? So let's say this is your actual barrier for your system. This is the profile, and you add extra potential, artificial bias potential, which is with shape and position chosen such as to exactly eliminate the barrier. Okay, so you would create something like that. You would have flat region here. If you manage that, then basically you remove barrier and sampling would be easy. This would be diffusion-like process. You would easily sample between reactant and transition and product. Okay, so bias potential, I need to say something about that this is an extra potential defined by user, and it's defined to act on some specified internal coordinates. once again, it's user who defines which internal coordinates one or many potential acts upon. VASP presently implements 3 types of bias potentials. It's harmonic potential, it's smeared step function, Fermi type function, and it's Gaussian potential. Now, well, you can choose the primitive coordinate associated with bias potential. Well, yeah, you can choose the coordinate. It could be either primitive coordinates, some simple function like Cartesian or fractional coordinates, interatomic distances, bonding angles and torsions, or even lattice vectors and lattice angles, lattice volumes and things like that. Or you can choose some kind of combination of primitive coordinates. So function of primitive functions, that's complex type. It could be sum, for instance, or coordination numbers or path-based coordinates, etc. So all that is supported now in VASP. Now, of course, when you add bias potential to your to Hamiltonian, to describing the energy of your physical system, of course, then you necessarily change statistics that comes out of your that is generated by your simulation, right? Because by modifying Hamiltonian, you basically modify this term in definition of probability density, for instance, and this probability density is in general different from unbiased probability density. But fortunately, the unbiased probability density that we are up to can be recovered exactly from in principle, exactly from the biased one, okay? And via a simple expression where only the terms computed from biased ensembles appear. Okay, this relation is so simple that I can't resist to derive it here. It takes only a minute. So let's start from unbiased probability distribution. Okay, with unbiased Hamiltonian. Here we expressed unbiased Hamiltonian as biased minus biased potential, plug it into formula, and this is what we get. Now we realize that the action of delta function here is that it selects out of all psi of functions of positions only those values which correspond to psi I. Okay, so when we do so, we can put this term into front of integral. Now we extend by unity. Okay, we multiply and divide by the same term, red one, and we realize that basically well, here, so this term is nothing but biased probability density, right? And this term here is nothing but inverse of expectation value of this exponential term. This is what we wanted to prove. It's very simple conceptually, right? So the method that employs this idea, right? So kind of eliminating effect of barrier by using bias potential is called umbrella sampling. But in practice, instead of guessing the shape and position of barriers and basically shape of position of corresponding bias potential, we proceed differently. We split the region we want to sample into narrower intervals, and we sample each interval separately. For each interval, we define its own bias potential. Okay, so the bias potential is usually chosen to be umbrella shaped. It is like umbrella shaped potential, umbrella shaped harmonic potential. Okay, so hence the name of method. Okay, so in bias potential, so in harmonic potential, the 2 parameters appear: force constant kappa and position of potential. By the way, it can be done, can be made time dependent, but that's not important. So this mistake that appears here. Anyways, it is essential to choose those intervals and bias potentials in umbrella sampling in such a way that the bias distributions that we generate in our sampling overlap. And the reason for that will become apparent in a minute. I wish to demonstrate the method on particular example. This is my toy reaction, nucleophile substitution of chloromethane. Here, one chlorine is replaced by another. Reactant is van der Waals complex. Reactant on the left, product on the right is just mirror image of product. And in transition state, this is perfectly symmetric state where bond on the left is being broken and bond on the right is just being created, and the two carbon chlorine distances are of the same length. Now, as a reaction coordinate, we can choose the distance between two chlorine carbon distances. As I told you, I mean, the choice of reaction coordinate or approximation to this is not easy in general, but I warned you, I mean, the coordinate will be given to us. Okay, so it is given to us at this moment, right? And with this choice, we have negative value for reactant and the same absolute, but and positive value of the same absolute value for the product, and zero value of reaction coordinate for transition state. That follows from symmetry of the problem. Okay, so here we go. Umbrella sampling. I performed 7 different molecular dynamic simulations with 7 different locations of umbrella potentials. Here they are. By that means I sampled these 7 regions. Here you see time evolutions of Xi parameter, which then and this data I then used to compute biased probability densities shown here. Notice how these probability densities overlap, right? This is important. Now, using the formula that we just derived a minute ago, we convert biased probability densities into fragments of unbiased probability densities, right? Okay, and finally, we convert probability densities into free energy fragments. And now we make use of the fact that the probability densities overlapped. Therefore, also free energy fragments should overlap too. Okay, so we can match this. This is the information we can use to match these fragments. Okay, I did so here, and I reconstructed a free energy profile. Okay, notice here that free energy minimum basically also coincides with maximum of probability density for parameter Xi that I computed in an independent, unbiased molecular dynamic simulation, as it should. Okay. Now I did this fragment matching in a naive way. I just wanted to demonstrate how things work. So I thought that it's the best way to show you how the procedure is meant. But in fact, you can do this more effectively. You can formulate this fragment matching as regression problem, and you can solve it without really human intervention, without, I mean, manual labor. Okay, and this is done in a method called weighted histogram analysis method. But I'm not going to talk about it. This is just a way of post-processing. Okay. Another simulation method that is based on the same idea using bias potentials, but differs radically in the way how post-processing is done. So the another method is umbrella integration technique. Okay, so here we use, it's important that we use bias potentials with very large force constants. So on these 2 plots, I compare bias potentials using umbrella sampling and here an umbrella integration, and you see the force constant here is like factor 50 larger in this case. This is important because what we want eventually is to generate biased probability distributions that are as much normal as possible, let's say. Okay, so we want to generate something that is Gaussian distributed, and this can be ensured by using large force constants. So notice that in this case, unlike in umbrella sampling, in umbrella integration, we don't need overlapping distributions. That's because in this method, we don't try to reconstruct free energy in that way. Instead, we compute free energy gradients. Okay, and Kestner and Thiel, these are authors of this beautiful method. They showed that free energy gradient for the point located at average of reaction coordinate for the given window, okay, psi bar. So the free energy gradient equals minus force constant times average psi minus position of given bias potential used in the sampling for a given window. Okay, so here I apply the equation. Here I plot free energy gradient as function of psi. And then this can be turned into free energy profile just by integrating gradients over reaction coordinate. And this is what we get. Yeah, I almost forgot to say, notice that for reactant and transition state, free energy gradients vanish or nearly vanish here, as they should, because free energy transition, both initial and final states were chosen to be stationary states, right? So this is pretty much like force in relaxation. Okay, so here I integrated, I recovered free energy profile, and I compare it here with free energy profile obtained in umbrella sampling. So black, it's integration, red, sampling, and you see that the two resulting profiles are well, almost identical, as they should. Okay, so I will talk about several different free energy methods based on different ideas, but nevertheless, the central idea, well, they are all based on physics, okay, on the same physics. So the predictions different methods make should be identical within some statistical uncertainty, provided everything is well set up. All right, so another method based on integration of free energy gradients is blue moon ensemble technique. Okay, but here instead of using bias potentials, we rather use hard constraints, geometry constraints, or holonomic constraints, if you wish. So in VASP, you can generate, you can define constraints essentially for the same type of coordinates as discussed in context with bias potentials. Okay, so once again, in constraint molecular dynamics, the parameter is fixed, strictly. Okay, so it only changes within some machine precision or within given tolerance, but it should not fluctuate as in the case of using restraint, so using bias potential. Constraints are implemented via shake algorithm. This is done by adding this extra term to Lagrangian describing the dynamics of your system. And this term consists of sigma, that's constraint function, and lambda is Lagrange multiplier determined iteratively during the procedure, during the shake algorithm procedure. Now, the lambda parameter actually corresponds to restoring force, or generalized force acting on internal coordinate, right? So in order to preserve the value of some constraint parameter, we have to add to physical force, we have to add some extra force called restoring force. Okay, this is expressed in terms of lambda parameter. So whole is acceleration times delta t square. And from this expression, you see that lambda is nothing but a generalized force acting on external coordinates. So no wonder it is also an essential ingredient used to express free energy gradient in blue moon ensemble method. So in practice, in blue moon ensemble, so blue moon ensemble simulation consists of series of constraint simulations, which are performed for different points or slices of configuration space around perpendicular to reaction coordinate. Okay, so differing in the value of psi. Okay, so from each such constraint molecular dynamics, you get free energy gradient, which you then integrate to get free energy profile. Yeah, this is just a remark here. So having determined free energy profile, it looks like that. Okay, and so performing simulation for transition state, constraint simulation for transition state, you get ensemble of transition state that you need in calculations of the velocity term. And in the case of blue moon ensemble method, this calculation can be done very comfortably, because it can be shown that this term can be expressed as so using constraint average of this inverse mass metric tensor, which is one of ingredients used in free energy gradient calculation. So this is basically printed in the output for every MD step, so you can very conveniently compute velocity, in post-processing and Blue Moon ensemble calculation. So that was just a side remark. Another method based on integration of free energy gradients that we have in VASP is steered dynamics, but here instead of sampling configuration space for different values of Xi, so we increase in this method the value of reaction coordinate continuously at some controlled velocity Xi dot. Okay, and we do so we start with some value characteristic for the initial state Xi A, and end in the final state Xi B, right? So then the work, irreversible in general, for such a transformation can be expressed using this equation. So it's integral over time, where here we have the transformation rate that we set. The user sets this, and this is generalized velocity for internal coordinate. Now we know from second law of thermodynamics that if this is okay, so if we average over work computed like that, for many processes realized like that, we should get the number that is greater or equal to free energy, and equality holds only for reversible transformation, that is for infinitesimally slow transformation. In the variant of method that we call slow grow method, we try to achieve or get sufficiently close to this reversibility limit. Okay, so here we attempt to realize the transformation so slowly that the work that we compute is good approximation to reversible work. Okay, a radically different strategy can be designed based on similar idea, transforming states at some constant rate. It is identity by Dzerzhinsky, which converts. That's formula by Dzerzhinsky, which converts this inequality into equality. Okay, so you can access reversible work basically by exponentially averaging irreversible work. Okay, and based on this idea, you can design a little bit different simulation strategy. So instead of trying to realize the transformation slowly so as to be close to reversibility limit, you don't care about that. You do transformation quickly, but you do so many times. Okay, and each time you get irreversible work, which you then average. So you have to repeat this many times, and then you average over the values you do. Okay, I have never performed this kind of simulations, but it is possible in principle. So be my guest and do so, and let me know how it works in principle. Instead, I'm using slow grow version of simulation protocol, and you'll have chance to try it out on our hands-on session on molecular dynamics. This is the next planned hands-on session. So this is what you get. So you'll monitor essential component of free energy gradient. So you monitor it as it changes in time, but since Xi changes in time at constant rate, you can plot free energy gradient versus Xi. This is how it looks like. It's noisy, but when you integrate it out, you get pretty smooth estimate of free energy profile. Okay, so the last free energy method designed specifically for rare events is metadynamics. Here again, bias potential is used as essential ingredient, but unlike in umbrella sampling and umbrella integration, you as user, you don't provide this bias potential. Instead, metadynamics build it for you, builds it on the fly in adaptive way, right? So it uses adaptive time-dependent bias potential, which is constructed as a sum of small Gaussian potential functions, so which are characterized by height h and with parameter w. Okay, so this bias potential is updated at a constant increment tg. Okay, this is what you do. So therefore, the number of Gaussians progressively increases during the simulation. This is how it looks like. So this is basically how bias potential is updated during simulation upon depositing this number of small hills, Gaussian functions. So we start by sampling reactants, basin, right? At every visited place, we deposit small Gaussian until we fill out the reactants basin completely. Then we start sampling product part, and once this is filled out completely, then we just switch there and back. Okay. Now, in the limit of infinite simulation time, the bias potential exactly counterbalances the free energy profile. Therefore, negative image of bias potential represents, and as in real simulation, finite time simulation represents an approximation to free energy profile. Okay. Now here you can see how a reaction coordinate parameter changed during simulation. The sampling of reactant. Here we switched cross transition state, its product, and recrossing, and then we freely shifted there and back. And here you can see estimate of free energy profile after first crossing of transition state, this point, that's black curve. Of course, here we sampled only 1/2 of profile, so here we have sampled only reactants part. Then after the second, so crossing, so recrossing of transition state, that's red curve here. And finally, after completing whole this run, 6,000, I think depositing 6,000 hills, yeah. So much longer simulation time, and you see that, I mean, from this point on, the profile didn't change much. So this diffusion actually didn't add any significant information, right? So in order to obtain a accurate result, reasonably accurate result, you have to use very small Gaussians, right? Well, but of course, the smaller Gaussians, the longer you have to wait till you fill out reactants and product basins. Okay, so therefore you can think of different strategies. You might start with, cursor sampling. You might start with bigger Gaussians, and after recrossing, you might reduce the size of Gaussians. That's one strategy. Or you can quickly sample with using, large Gaussians, and then refine your results by using other methods, like more effective methods like umbrella sampling, for instance, as suggested by Ensing. As I already complained, in many cases, a reasonable approximation for reaction coordinate is difficult to identify, right? But still, as a set of, say, m parameters forming basis set for definition of assumed reaction coordinate can be identified. Think of process, for instance, where you, break 3 chemical bonds, and at certain point you form another 2 chemical bonds, and well, this process doesn't happen all in the same time. So there is certain sequence at which bonds are broken and created. Okay, and for something like that, it's pretty difficult to find an analytical function which describes that all in right progression. But clearly, that these 5 bonds, 3 that are being broken, 2 that are created, are somehow involved. Okay, so you might reasonably well assume that these 5 bonds will form certain basis for some unknown reaction coordinate. Okay, and metadynamics can handle this kind of cases. Okay, cases where you can only define basis for unknown reaction coordinate. In this case, metadynamics creates bias potential that acts on all degrees of freedom that you specify here. And the bias potential kind of pushes the system against the path of least resistance, so to say. Okay, and in analogy to metadynamics with one collective variable, what we obtain in well-converged metadynamics is a negative image of free energy, but it's not profile anymore. It's multi-dimensional object, so it's rather hypersurface rather than profile. Okay. Let's see how it works. So let's come back to our toy system, and let's use the two distances R1 and R2 as two independent collective variables. Now this is how it works. So we sample reactance basin, but now we are in 2 dimensions, and due to increased dimensionality of problems, so also the volume of that is to be filled out, the volume of basin for stable state also increases. So therefore we have to wait longer till we fill out the corresponding basin completely. We have done so already, so we are now sampling the products part. Okay, and I will perhaps accelerate it. And from some point on, we just, as before, we just move there and back in diffusion-like manner. This is the resulting 2-dimensional free energy surface that I obtained. That's a function of R1 and R2. And one should keep in mind that, yeah, this object is not quite the same thing as the one that we obtain in 1-dimensional case. The two objects can be, I mean, you can recover profile from free energy surface. Nevertheless, it is not exactly the same thing. They are related, but they are not. So it would be a big mistake to deduce. So to compare results obtained using different number of collective variables, as is unfortunately done in the literature. All right. So in all methods that I have discussed up to now, we needed one way or the other to consider transformation path from initial to the final state, and these might be these disadvantages in some cases. Think of adsorption problem, for instance. Okay, so you want to compute, let's say, free energy of adsorption, so you need to compute the free energy difference between desorbed and adsorbed state, right? Now, should you consider a whole transformation path, you would really need a huge structural model, because let's say you want to you have substrate with internal volumes like zeolite, and you want to adsorb inside a bulk of material, let's say. Okay, so of course, evidently you need sufficiently thick slab model so that you achieve bulk limit, right, somewhere in the middle. Plus you need very wide vacuum gap in your simulation cell, so that for a desorbed state, for initial state, adsorbate it's sufficiently far away from surface, that is, so that it is not immediately attracted by it, right? So it's reasonably independent of it. I mean, that would be very inelegant to perform such a simulation, right? Here I would like to talk about the method that allows you to overcome this problem. That's thermodynamic integration with harmonic reference. Here, the free energy of an interacting system that I label 1 can be written as free energy of harmonic system, 0, plus the difference, unharmonicity. Okay, so now advantage of this formula is that this term, harmonic free energy, can be expressed analytically. You can use quasi-classical or quantum mechanical expression, which depends only on energy of minimum and harmonic frequencies in principle and temperature. Right, so this is something you can compute easily in static calculation. And the unharmonicity correction, this comes from thermodynamic integration. Okay, and the integration is done over a variable lambda, which is the coupling strength between harmonic and fully interacting system. Okay, so for lambda 0, okay, so and the integrand here, that's the difference between potential energy for fully interacting and harmonic system. Okay, and the integrand is computed for different values of lambda, and this notation here means that ensemble is computed in molecular dynamics driven by some classical Hamiltonian that is expressed as a mixture of fully interacting and harmonic Hamiltonian. Okay, so this is the way how you can switch on basically anything behind the harmonic. So all interactions be beyond the harmonic approximation, right? So I mean, this is quite classical theory, well known in the business, but sometimes classically it is formulated in terms of Cartesian coordinates, which makes it difficult to perform simulations of, let's say, free molecules or highly mobile fragments, or something that rotates. Okay, so that's the problem. So together with my colleagues from Karlsruhe, Felix Stutt, Philipp Lessow, and Jonas Amsler, we propose to formulate a problem in terms of rotationally and translationally invariant internal coordinates to overcome the issues that I mentioned earlier. So now we are able to make these kind of simulations also for free molecules, for instance. This is a little demonstration. That's argon dimer. Here, this is quasi one-dimensional problem because well, it can be represented. I mean, the whole problem can be formulated only in terms of one single internal coordinate, which is just distance between two argon atoms. Now, since the dimerization energy of argon is very small, it's only 15 millieV. Okay, you can expect that the dimer be unstable at room temperature, which we considered in our calculations. Clearly, harmonic approximation is unable to take this into effect, this instability. Look at the comparison of full potential black line with harmonic potential here. You see that harmonic potential, works reasonably well only for narrow region and around the minimum. Okay, for larger values, for larger distances, it increases too steeply, and for shorter distances, it actually increases too weakly, right? So, but evidently, whenever you try to make dimer collapse, you hit on this steeply increasing region, generating restoring forces, which basically restore dimer. So under harmonic approximation, you won't be able to basically destroy dimer by thermal motion. Okay, so this is the problem that we considered as as our test case of our implementation. So we computed anharmonicity in series of NVT, molecular dynamics calculations for different values of lambda. Okay, so these are values of integrand. When we integrated over lambda space, we got this value. The negative sign here makes perfectly sense because, of course, whenever, as I told you, the dimer is expected to be unstable at its temperature, and whenever you basically destroy dimer, you convert vibrational degree of freedom into something soft, in some kind of hindered translation, let's say, which is always linked with increase in entropy and therefore decrease in free energy. So, I mean, just common sense tells you that this is a reasonable number, but we were able to, to test it more rigorously because this is a one-dimensional quasi one-dimensional problem. So in principle, having analytical expressions for full and harmonic potential, you can find analytical expression for integrand, and you can obtain accurate reference value for free energy difference, for anharmonicity. And you see, we got the reference value is pretty close to what we got. This is a real-world application of the method. That's adsorption of argon in zeolite shabazite at 200 K, right? So free energy of adsorption is not easily accessible experimentally, unfortunately. So therefore, it is desirable to have reliable theoretical tool to predict that. Okay, so in this particular case, we were lucky to find a good experimental reference. This is Gibbs free energy of adsorption for argon. And so theoretically, this Gibbs free energy of adsorption can be computed again from free energy differences between substrate plus adsorbate minus non-interacting systems, right? And we did so at PB plus D2 level of theory. Okay, harmonic approximation, as I told you, necessarily fails because as you can see here, this is radial distribution function computed under action of harmonic potential. Harmonic approximation actually confines argon to the vicinity of adsorption, so adsorption site. Argon never escapes, right? But so therefore, a harmonic approximation gives you a totally wrong prediction. Even sign of that is incorrect, as you can see. Now, well, running simulation with fully interacting potential, we see that argon indeed is, I mean, this adsorption complex indeed is not very stable. There is great likelihood to find it far away from adsorption site. Okay, therefore, when we performed the accurate calculation, we found that the system wins some extra entropy, lowering thus adsorption free energy, and the result that we got is pretty close to experimental estimate. All right, I think I still have some 10 minutes. So this brings me to, I think I have to accelerate a little bit. So this brings me to the very last part of my presentation. Here I would like to say a few words about making molecular dynamics simulations more effective, okay? So today, ab initio molecular dynamics can be quite routinely performed for systems of up to 1,000 atoms. But still, these kind of simulations are very time consuming, okay? And well, these of course make us, so these CPU requirements, CPU time requirements make us to make often serious compromises in the simulation time and in the choice of structural model quality, right? Furthermore, due to high CPU time cost of molecular dynamics, the calculations are only rarely performed at different levels of theory, as is quite common in the case of static calculations, where very often people perform simulations in series for different levels of theory and picking up basically or identifying method that works best for their problem at hand. We are lacking this kind of information for molecular dynamics. So basically, we don't know how different functionals perform in temperature-dependent problems, for instance, right? Yeah, so now recent developments in machine learning technology for chemistry and material science offer an opportunity to overcome some of those problems. The MLFF method implemented in VASP is based on the adaptive on-the-fly learning, is an extremely efficient method for accelerating molecular dynamics. You can boost your simulation by a factor of 100 or more, and you'll have opportunity to try it out in the next hands-on session, I guess. And you will learn more about the theory behind in the next lecture of Professor Kresse. Okay, alternative machine learning can be also coupled with perturbation theory to address the other problem, so to effectively determine properties at multiple levels of electronic structure theory. And this is something I would like to talk about. This is work done in close collaboration with Professor Dario Rocca from University of Lorraine and his team. Okay, so this is the MLPT approach. Now, suppose that the free energy of activation has been already computed at certain level of theory, which I will call from this point on production method. Okay. And suppose that blue moon ensemble approach was used. Okay. Now the question is, can we predict the same quantity, free energy of activation or free energy difference in general, for another possibly more demanding method for which maybe even analytical gradients are not available, and that method will be termed target method here. Okay, and can we do so without repeating all the time-consuming molecular dynamics simulations? Okay, now the key observation here is that the data produced in molecular dynamics in sequences that are shorter than correlation time, which is typically of order of, let's say, 100, few tens or hundreds of femtoseconds. So those data within these short sequences are not independent. They are time correlated, as we already discussed. Okay, so in some sense, we are, investing a lot of time, wasting time, if you like, into propagating system in time instead of really generating independent data, improving our statistics, right? But look, once we already performed the simulation at certain level of theory, we already propagated it in time. So perhaps there is a way how to somehow reweight statistics in umbrella sampling-like fashion, maybe, right? Somehow, and somehow be able to deduce. So only repeat the calculations at a higher level of theory, only for reduced number of points, right? So this is the idea which my observation here suggests. Now, since the target method and production method Hamiltonians are supposed to differ only in potential energy, so to distinguish target method and production method quantities, I use tilde for target method. Okay, and here in this equation, I also define what I mean by delta V, difference in potentials here. Okay, so since they differ only in potential energy, it can be shown that the following exact relation between the respective partition function holds. This is pretty much similar, analogous to what we derived for umbrella sampling, and this idea comes back to 20. This was formulated in the middle of 20th century. It's a pretty old idea, right? Having performed simulations at production method level, we are able to restore statistics at target level method, provided we can compute the difference in potential energies between these two. And importantly, the ensemble average is done at production method level only, right? So you don't have to produce extra molecular dynamics for that. Okay, so having expression for partition function, you can plug into definition of Helmholtz free energy, and this is what you get. This is a relation between target and production methods free energies plus correction term. Okay, now this is the idea coming back to 20, free energy perturbation theory, and this level of theory applied to Blue Moon ensemble method results in this simple expression. Once again, this is target method activation energy, production method activation free energy plus two correction terms for transition state. This requires computing ensemble, constraint ensemble in transition states, ensemble average for transition state, and correction term for reactant. This is this term here. Now we already achieved something, because you see that unlike in the Blue Moon ensemble method, we don't have to drag the system all the way from reactant to transition state. The correction only have to be done for initial and final state. So that's already some achievement, right? Now, according to this recipe, additional single point calculations have to be done in order to compute delta V's, okay, for transition state and reactants configurations, right? Now the question is, so if only a small number of target method calculations can be afforded, can we still use free energy perturbation theory? Let us test that. Okay, let's test it on toy system again. That's the proton transfer from oxygen O1 to oxygen O2 in zeolite Shabazite, reactant, product, and transition state. As production method, I used cheap PBE. As target method, I used quite time-consuming hybrid functional HSE06. By the way, for this particular system, HSE06 single point calculation is about factor 50 more time-consuming than PBE. All right. Okay, and now let's assume that we want to apply free energy perturbation theory, but we can only afford 50 extra calculations for each correction term. And let's focus on correction term for transition state for a while. Okay, so in this numerical experiment, I made 50 random choices, okay, of configurations generated at PBE level, and computed correction term. And I was interested in quality of prediction and also in uncertainty. So I repeated the selection of random selections 100 times independently. Okay, so every single point is a result of such calculation. So you see, and the dashed line here is exact reference that we were able to compute. I'm not going to talk about that. As you see, even with small number of configurations, the results are distributed around the correct reference value. Nevertheless, the uncertainty in predictions is very large. It's like 0.1 EV, which is as large as the correction itself. So, I mean, you see that the naive free energy perturbation theory with such small number of configuration is not very effective, as expected. But the formulation of the problem literally calls for the use of what is called delta machine learning. We are learning differences in physical property instead of the physical property itself. Okay, so instead of learning HSE06 potential energy, we are just learning difference between HSE06 and PBE. What's the advantage of it? The thing is that both functionals actually describe large part of physics in pretty much the same way. And in fact, they differ only in details. And this is exactly what we try to learn. Okay, these differences. Okay. Now, a separate model has been trained for reactant and transition state. So we don't need a robust model describing whole configuration space. We need focused model which works well for individual states. Okay, and our strategy is that instead of using 50 configurations in this numerical test in free energy perturbation theory directly, we instead train machine learned model and use it to predict differences in potential for every configuration. And this is then used in a calculation of correction. This is the result of such a calculation, green points, and you see that we achieved that the uncertainty was reduced pretty much. This is now narrow, but still we see some problem. We see there is systematic error. The green points are systematically shifted. They are above our reference line. Okay. Clearly, this comes from the systematic error of our machine learning model. We still used a relatively small number of training set members, right? So we are able to express correction for this systematic error. Okay, so to do so, we need to define a small correction set on which we evaluate errors for individual configurations. This is mean error, root mean square error, and some covariance. And using this correction, we can basically we can get pretty close to the reference line. Such correction works surprisingly well also for much smaller training sets. So you see here, this is size of training set we used in machine learning. This is the reference value, and you see that already for the smallest training sets, we got quite accurate result with relatively small uncertainty. But best of all, you don't even need to compute this kind of correction in many cases. In particular, when the quality of a machine learned model trained for transition state and reactant is comparable, and also the correction would be of about the same size. And because of the formulation of problem, if this correction delta is about the same, so well, it will cancel the contribution for transition state, and reactant would cancel, right? So and that's the reason why the final quantity we are interested in converges much faster than actually individual ingredients that we have here. So I think I will terminate here.
Okay.
Let's discuss.
Great. Thanks a lot for giving also people the opportunity to ask some questions. So it's about the Langevin gamma and the PMAS. When you do trial and error, which output values should you look at to judge whether your calculation goes well, whether you selected the correct parameters?
Okay, so I will open it. So yeah, here. So for Raman Parinal method, enthalpy is a conserved quantity. Okay, so VASP automatically computes that for you. So this is what you see in OSICAR, for instance, directly. So so first of all, when setting W value, what you can still do is basically monitor the conservation of enthalpy, right? That's one thing. The other thing is when your W value is too small, okay, so then you most likely you will have convergence issues because you have simply too fast oscillations, so you're likely to generate unphysical configurations. Okay, and I mean this is something you notice very quickly, right? And otherwise, I would say, well, it's what you should look at is basically your quantity of interest, okay, and look at how sensitively or well, what is let's say wavelength of oscillations of your quantity of interest, and by adjusting W, you can make it, you know, so if you set smaller value, everything oscillates faster, and therefore the quantity of interest might converge quicker. So you might want to try to set W to be as small as possible while maintaining the stability of algorithm, right? So something like that. And for the other parameter related to thermostat, so here, of course, this affects basically how aggressively you're thermostating. Most of work actually is done by atomic degrees of freedom. If you have sufficiently large system, you can basically set the friction coefficient for cell parameters to 0, right? Because well, the system is coupled. I mean, the cell parameters are of course naturally coupled with atomic degrees of freedom. So you are thermostating atomic degrees of freedom, and they can also thermostat cell degrees of freedom. Okay, so for large systems you can do so, and you can still monitor instantaneous temperature specifically for cell degrees of freedom. This is written in VASP output in a report file. You have separate temperature contributions for atomic and lattice degrees of freedom and the overall temperature for extended system. And if you see that you don't have good control over temperature of lattice degrees of freedom, there are only 6 independent degrees of freedom. So the fluctuations are typically larger, of course, but if on average your cell degrees of freedom temperature deviates significantly for desired temperature, you might introduce more aggressive thermostating. Okay, so then you would increase the Langevin, how is it called, gamma? I don't know, I forgot how it is called for lattice degrees of freedom, but there is a specific parameter for that. So, well, I would start with, okay, so assuming your system is large, let's say 100 atoms or larger. So I would start with 0 value, let's say. I would thermostat only with atomic degrees of freedom. I would monitor temperature of lattice degrees of freedom over short simulation time, right? And if I see that my average temperature is very different from desired temperature, I would increase that friction coefficient. So unfortunately, it's still trial error procedure.
Yeah. Thank you. So if you allow, then I would ask one more question that is related to the MLPT that you just talked in the end about. So in case of corrected MLPT, can we say in layman terms that we have the potential energy from the production method at different time steps, and we are interpolating the difference between the energy in target and production method using machine learning?
Yeah. So we basically work with ensembles of configurations generated at production level of method, okay? And in principle, ideally for each and every configuration, you would like to compute delta V. But in order to compute delta, you already have energies for production method because this is in your output from molecular dynamics, so you already have that. But you still need to compute target method, potential energy, right? It would be too expensive to, compute that explicitly for every single configuration. So the idea is that you only select few configurations, use that information, you compute delta V, use that information to train machine learning model, okay, and use that to predict delta V for the rest of ensemble, okay. This is the idea.
So concerning the machine learning model, are there physical constraints on that? So, for example, any kinds of invariants that we expect to be present in that system?
What for? Sorry, I'm not
sure. So, is there any
point.
physical constraint on the machine learning model of a correction which is used for difference between the production method and the target method?
None that I would ever of. Okay, so basically, this is okay. So this is quite a general idea, right? So basically, you can. I didn't say much about how the machine learning part is actually realized in reality. And well, here we basically use pretty much common tools available on the market. Okay, so we use pretty standard libraries that are presently available, and but this is not a unique choice. You can experiment also with other technologies, right? So we use kernel-rich regression model and use very usual SOAP descriptors, which also MLFF uses, or well, variants of which VASP uses too. And well, but this could be replaced also by other descriptors and other regression models. Okay, so this is pretty general. So we didn't experiment much with that. Okay, so what we used worked pretty well out of box. So we didn't have to deal with that, and I'm not aware of any constraints.
I hope we answered the question from the audience with that. And actually, I would like to thank you again for the great talks, and also for staying a bit longer to answer the questions. So thank you very much.
All right. I thank you.